Swayam Prabha. Digital India. Educated India.
We will resume our discussions on MD simulations. So far what we have done is to describe the MD simulation of a liquid argon. Then we considered simulation on water molecules. Then we also considered mixtures of water and alcohol. Today we will resume our discussion on MD simulations of an s-peptide. S-peptide is a collection of amino acids, and Sonanke will describe how to go about this simulation. Can you start?
Yeah. So today we'll do the MD simulations of s-peptide. So what we'll do here is, first we'll create a topology file from a PDB file, and then we'll create a periodic box around the s-peptide. We'll also solvate it, and then we'll perform energy minimization and full molecular dynamics. And after performing full molecular dynamics, we'll try to analyze some of the properties of the s-peptide using the trajectory. So PDB file of s-peptide, we first need a PDB file, which is the protein data bank file of the peptide. So to view the PDB file, we'll view it using the command vi. So we have to type vi s-peptide.pdb, and after we type vi s-peptide.pdb, something like this will appear on the screen. So here we will see that there is one in the fourth column, there is one about for lysozyme, then there is glutamine, then there is tryptophan, then there are different amino acids, right?
So how many sites are there for LYS? There are about 6.
There are about 8 sites,
Okay.
8 to 9 sites for lysozyme.
Okay.
Then there will be another amino acid, glutamine.
Okay.
Then there will be alanine.
So this s-peptide.pdb, they have to download from
the RSCB side, from the protein data bank side.
Into their directory.
Yeah, into their directory they have to download it.
Okay.
So this is the PDB file of the peptide, right? And after viewing the PDB file, so we'll create a topology file using the PDB file. So to create a topology file, we'll use the command pdb to gmx, right? So first we'll type pdb to gmx minus h is the help command. So first we'll see what the command does. So after you type pdb to gmx minus h, it will display what are the input file that is required to run this program, what is the output file that we expect from this program. So we see that the input file required for this program is the PDB file, which is the s-peptide.pdb, which we already have. And the output file, we can get a topology file, we can get a GRO file, an index file, and ITP file. So
what
now,
is that clean.pdb?
That is a PDB file format,
Okay.
in a different format.
Okay. Minus q, that is the option, no?
Yeah,
Last
that
one.
is the option.
Okay.
So now we'll type the command pdb to gmx space minus f s-peptide.pdb, which is my input file, then minus p s-peptide.top, top is my topology file for the peptide, and minus o s-peptide.gro, which is the Gromacs structure file. So here s-peptide.pdb is my input file, and s-peptide.top and s-peptide.gro, these two are my output file. So after I type the command, something like this will be displayed in the screen, which will ask me to select a force field from a number of force fields that are already given. There is amber, charm, gromos, OPLS, there are all kind of force fields that are available. So we have to select one force field. So
You just have to give the number of the force field?
yeah, we just have to give the number of the force field. So we choose 9 here. So and 9 is the Gromos force field, Gromos 43A1 force field. Similarly, one can choose different force field as well. So I have chosen the Gromos force field.
And all the references are given there from where
Yeah,
these
the references
things
are given
taken.
there. Yeah.
Okay.
So after I choose force field, then it will ask me to select a water model. So select the water model. So I choose one, which is the SPC, that is a simple point charge model. And now I'll have my s-peptide.pdb and s-peptide.gro file. Now what I have to do, I have the PDB file in a box. Now I have to solvate the peptide. Now to solvate the peptide and to create a box, we will use the command edit conf and genbox. So by using edit conf, it will make a box with the user specified size around the peptide. Whatever the box size that we give, it will create a box around the peptide using that box length.
The coordinates of s-peptide are already assigned.
The coordinates are given in the PDB file.
So they are already taken in that other files which were the output files?
In the GRO file, yeah. From the PDB file only the GRO file is generated. Correct. So the coordinate will already be there in the GRO file.
And it usually puts it in the center of the box?
Yeah, that you have to specify.
Okay, that you will specify later now?
Yeah, right now I will specify it. So to generate a box around the peptide, we will type the command edit conf space minus f s-peptide.gro, which is my Gromos structure file, minus o is the option for output file, out.gro is my output file, minus d 0.5 space minus c. So what is minus d? Minus d is the distance between the solute and the box, and minus c, it specifies centering the solute molecule in the box. So by giving the command minus c, I am giving the command to that my peptide has to be in the center of the box.
So that minus, instead of minus c, what are my options? Can I give some?
Then you have to specify the coordinate. Then you have to give the coordinate.
X, Y, Z.
Yeah, x, y, z. Then you have to specify where do you exactly want your peptide to be.
Okay.
So now that I have my GRO file and I have my box around the peptide, I'll now solvate the peptide using the command genbox. So after edit conf command, you will get something like this, where you will have your system size, center of the box, box vector, box angle, and all this stuff. So now now genbox, it will read the structure file, that is the out.gro file, and it will fill the box with water. So the command is minus genbox minus cs spc 216.gro, which is the water model that I will be using to solvate my peptide, minus cp out.gro, out.gro is the peptide and within the simulation box, minus p s-peptide.gro, and minus o conf.gro. So minus cs, it specifies the solvent structure input option, minus cp is the structure file input option for the solute molecule. Right. So after you give the command, something like this will be displayed in the screen, where it says that added 850 molecules. So it will add 850 water molecules in the simulation box, and it will also modify the topology file, because initially when we have generated the topology file using the PDB file, only the peptide was there, but now I also have water in my simulation system. So it will add the topology file for water also in the top file.
What was the box length that was given for this calculation?
I didn't give any box length, so it has taken the box length according to the size of the peptide.
Okay.
I have just specified that the distance between the solute and the box has to be 0.5, and that the solute has to be in the center of the box.
Okay.
So it will take the box length according to the size of the peptide.
Okay. But it has given the volume now.
Yeah.
So from that volume, the cube root of that volume should give me the length of the box.
Yeah.
These are all cubic boxes?
It may or may not be a cubic boxes.
Okay.
Because to specify a box type, then you have to give minus dodecahedron or minus
but
cubic.
But now it says box angles are 90, 90, 90.
Yeah.
So I expect that to be a cubic box.
Yeah.
Okay.
So there is a slight error in this. Minus p s-peptide, instead of GRO there will be top, because minus p is the flag for topol.top option.
Okay. So instead of s-peptide.gro, it should be s-peptide.top.
Top, yeah.
Okay, on the right, extreme right.
Yeah.
Okay.
So now it will also modify my topology file, right. So if I just type tail s-peptide dot top, it will take me to the last few lines of the topology file, right, and something like this then will be displayed in the screen, that there is protein, there is one, that is my s-peptide, and salt, that is my solvent molecule. There are total 850 solvent. Initially when we look, when we have a look in the s-peptide dot top, when we generate it using the command using only the PDB file of s-peptide, we will just have protein in the PDB file, in the topology file, we will not have solvent.
So this 850 is the number of molecules.
Number of solvent molecule that has been added in the simulation box.
Okay, then the number of atoms for water will be 3 times 850.
Yeah, 3 times 850, and total number of protein.
And whatever number of atoms associated with that protein.
Yeah, that will be in my GRO file.
Does it display that also, number of atoms in a protein?
Yeah, but then you have to open the GRO file to have it. So now that we have protein and solvated protein, we have the topology file, and so now we will proceed towards the energy minimization of the overall system. So for energy minimization, we will need 3 files, that is the GRO file, we need the TOF file, and we need the energy minimization molecular dynamics parameter file, that is the em.mdp file. Now to perform energy minimization, we have to first generate a TPR file. So first we will type the command grompp space minus f em.mdp, which is my molecular dynamics parameter file for energy minimization, then minus space minus c conf.gro, which is my GRO file including my solvent and the peptide, then space minus p s-peptide.top, which is the topology file, and then space minus o em.tpr, that is my output file. So after generating em.tpr, now we will use this TPR file for the MD run for energy minimization.
So when it does the energy minimization,
yeah,
does it tell you how many steps it did, or it just?
Yeah, it will display on the screen that how many steps did it take to perform the energy minimization.
And whatever constraints you have put for minimization, that also it will display.
Yeah, it will display the value of force.
Correct.
At what step it stopped energy minimization, it will display everything. So next command is md run space minus v space minus deff_nm space em. So what minus deff_nm does, it will generate all my output file, that is I will have a different GRO file, I will have a TPR file, I will have an XTC file, it will generate all those files using initial as em.
Okay.
So something like this will be displayed in my screen. So as we can see there, it took 19 steps to perform energy minimization, and at each step it has written the potential energy, total force on which atom. So my final potential energy is minus 3.08 into 10 raised to the power 4 kilojoule per mole. So this is the value.
The maximum force is also written to the right.
So
initially the maximum force was very large.
Yes.
Now finally it has become small.
Yes.
And it is writing the atom number on which the force is the maximum.
Yeah.
Okay.
So now since my energy minimization is done, so in this case, when you have a large molecule like peptide and protein, so you have to do a position restrained MD. What it does is, a part of the system is not allowed to move, right? So what we do, we restrain the position of the peptide and we allow the water molecule or the solvent molecule to equilibrate around the protein. Yeah. So we have to modify the s-peptide.top, that is the topology file, accordingly. So we just have to add 3 lines there, that is position restraint.itp file. We just have to add this position restraint itp file in the s-peptide.top file.
So in this file, all the atom
of the peptide
which
are
have to be kept fixed are given there?
Yeah, that is the peptide has to be kept fixed, and we will allow the water molecules.
So are you fixing all the atoms of the peptide or some of them?
All the atoms of the peptide.
Okay. Okay.
So similarly,
but is it possible to do it with some atom fixed, some moving, or that is difficult?
Yeah, that is also possible. Then you have to specify those particular atoms in your ITP file.
Okay.
So now to perform position restraint MD, we need the GRO file from energy minimization. We need the topology file, that is s-peptide.top, and we need position restraint MDP file, that is pr.mdp file.
So how is that created, pr.mdp?
You can, it's just same as full.mdp with some extra constraint added.
Okay. But that you have to add manually, or is there
Yeah, you can add manually. Even one can download it from Gromacs tutorial sites also.
So they have given that pr.mdp
They
files.
have given the format, what is the required format for that.
Okay.
So now to do it, here also we have to first generate the TPR file. So we'll use the command grompp space -f space pr.mdp. pr.mdp is the position restraint molecular dynamics parameter file. Then space -c space em.gro. em.gro is my energy minimized
Okay.
configuration. Then space -p s-peptide.top, which is the topology file. Then space -o pr.tpr. And this TPR file will contain all the information about MDP file, GRO file and the top file.
Is the order important? You have this -f pr.mdp.
No, the order is not important.
You can give in any order.
Yeah, the order can be anything.
So my first one can be -o pr.tpr
Yeah,
and the
it
last
can be.
one could be that.
Yeah, the order is not important here.
Okay.
Just the flag is important, that what flag you are using for what file.
Okay.
And after you generate the TPR file, you have to run the TPR file using the command mdrun. So mdrun space -v, then space -deff_nm space pr. So the only output file that we require from position restraint MD is the GRO file, that is the pr.gro file.
But many others will be created with
Yeah,
pr as
many
the starting.
Yeah, PR as the starting.
Okay.
So something like this will be displayed, that I have given total of 5000 steps in my pr.mdp file and my time step is 2 femtoseconds. So total mounting of 10 picosecond simulation. So it will display in the screen that how much time did it take to complete the simulation and all stuff. So once we do it in the terminal, then one will know that how it works.
Okay. But why is it showing 0 seconds everywhere?
Where?
Step 4900 remaining time.
That is the remaining runtime is 0 second.
That means it is finished.
It is almost finished.
Okay.
Yeah.
And what is that volume 0.781 on the 6% something?
That is how much space will it take in the disk to
Okay.
occupy all the files, output
Okay.
files. So once we are done with position restraint MD, so now we'll check the potential energy of the system. So to check the potential energy of the system, whether it has minimized or not, so we'll type the command g_energy space -f space pr.edr. pr.edr is the energy file which we will get by position restraint MD. Then space -o out.xvg. This out.xvg file will contain the potential energy as a function of time.
And what is that last one
Minus
W?
W.
What is
That
that for?
will display the graph.
Okay.
And then enter.
Okay.
So after you do this, you will be displayed with a number of parameters given here. So there is dihedral, there is improper dihedral, there Lennard-Jones, short range, long range, total energy, temperature, pressure, all these energy values you can calculate as a function of time. So what we need here is potential energy. So we see that potential energy is in number 9, right?
Okay.
So we'll first type 9 and then we'll type 0. So it will give me the value of potential energy. So
but where is that, go back, where is that 9 displayed there?
It's just
Third one.
in the third line.
Okay.
So 9th is the potential energy, 10th is the kinetic energy, 11th is the total energy.
Okay.
One can check these energy values as a function of time.
And what are those numbers on the third column?
Which numbers?
See, first one says, first one G9 angle.
Yeah.
The next one is proper
That is
dihedral.
the second one is proper dihedral.
What is the 3?
Third one is improper dihedral.
Okay.
Fourth one is, so if you type 3 and then 0, it will give you the value of improper dihedral as a function of time.
Okay.
Suppose if you type 12 and then 0, it will give you the value of temperature as a function of time.
Okay. And 4 and 0?
4 and 0, it will give the Lennard-Jones 1,4 interaction as a function of time.
Okay.
So this is what it
But
means.
does it also plot those things? You can plot if you want.
You have the file out.xvg, right?
Okay.
So if you have out.xvg, you just have to type xmgrace out.xvg, it will give you the plot.
Okay. First you do this type 9 and then 0,
Yeah.
then give that xvg.
Yeah.
Okay.
So after you type 9 and then 0, it will give the value of potential energy. So here you can see that the average value is given -37683.4 kilojoule per mole.
Okay.
You will also have the error estimate and the RMSD value as well.
And what is that total drift?
Yeah.
RMSD is the total Root means square deviation in the average energy.
In the average energy, and since we are just doing it for 10 picoseconds, so
Right.
my potential energy is very large, minus
So that
37,000.
total drift may give you the difference between the maximum and the minimum value
Yeah.
in that average,
Yeah.
around the average.
Yeah, and if we perform simulation for sufficiently larger amount of time, we will get a
Smaller and smaller RMSD.
Yeah.
Okay.
So after we check, we are done with checking the potential energy. Now we will perform MD without restraint, where we are allowing the peptide to move as well along with the solvent molecules. So what we do here, we need the GRO file from the position restraint MD. Then we need the topology file and we need the full MDP file. So here also first we will generate the TPR file using the command grompp space minus f space full.mdp, which is the molecular dynamics parameter file for full molecular dynamics simulation. Then minus c space pr.gro, which is my position restraint GRO file. Then minus p s-peptide.top, which is the topology file, and minus o, which is my output file full.tpr. This is my output file.
So what decides that there are no constraint in this command, or it is still with constraint, the present one?
That is without restraint. That is in the previous one,
Right.
we have restrained the position of the peptide, right, and we are just allowing the solvent molecule to equilibrate around the peptide.
Okay.
But now in the MDP file we will have a change. We'll change in the MDP file and then we'll allow the peptide to move as well. We won't fix it.
So what is it that is changed so that it knows
In
it
the
is not?
MDP in the full.mdp file, we have to give a command there. We have to add an extra line there, that which are the atom that you want to fix or which are the atom that you don't want to fix. So there's a difference in the pr.mdp and full.mdp file.
So this PR is different from the earlier PR.
This is a full.mdp file.
Okay. Okay.
So after my full.tpr file is generated, I will use it to run my MD simulation. So I'll type the command md run space minus v space minus DEFFNM space full, and then it will give the result of full molecular dynamic simulation. So I'll have trajectory file, I'll have TPR TRR file, and with which I can calculate potential energy, the number of hydrogen bond that the peptide is forming, and we can also plot Ramachandran plot, which is very important in peptide, which will show when we perform it in the terminal.
So do you have examples of that, some of these files here?
Like
Or we will show while demonstrating?
We'll show while demonstrating.
Okay. And what are some of the difficulties we come across when we do these things?
See, this is a large peptide, so while you generate a topology file, then you have to specify an n number of bond length in the topology file to create it.
Okay.
You may or may not have a topology file for a protein or a peptide, so you have to create it manually. You have to go add the bond length and bond angle in the bonded and non-bonded file, and from there you will generate a topology file. So it does give a lot of error while creating a topology file basically. And since it's a peptide, you have to do a long simulation. 10 picosecond is for just showing purpose that it is performed it will give me result easily, but to equilibrate it sufficiently,
So
since it's a large molecule, so you will require long simulation.
So at least say 10 nanoseconds or more than that?
Yeah, at least 10 nanoseconds or more than that.
And for the MD run, how much time
For
will it
MD
need?
run, maybe 15 to 20 nanosecond to get a good result, so that we can compare it with some experimental value if available.
Okay. And is there a separate file where the last configurations are saved? Suppose I don't want to do 50 nanosecond in one stretch.
Okay.
I want to do it 25 nanoseconds and 25 nanoseconds.
Okay.
How do I go about?
So what you can do is, first 25 nanosecond you are done with the simulation, right?
Okay.
And then you will have a trajectory file.
Right.
So you convert your trajectory file into a GRO file, and the moment you convert it, you will have configuration at each time step in that GRO file.
Okay.
So you can take the last configuration and then you can start simulation with that configuration, the remaining 25 nanosecond.
So the last configurations has to be put in some place which is the first configuration of the previous run.
Yeah.
So what is the procedure for that?
See, you will have a trajectory file from your 25 nanosecond simulation, right?
Okay.
So you convert your trajectory file into a GRO file, that is XTC to GRO.
One command is there?
Yeah, there is a command,
Okay.
trjconf.
Okay.
So you convert it into a GRO file. In that GRO file, you will have configuration at each time step.
Okay.
Right? Suppose you have given 2 femtosecond as a time step. So it will write configuration at 0 time step, then after 2 femtosecond, then after 2 femtosecond till your last time step. So you take the configuration of the last time step.
Correct.
And then you start from there. In that file, you will have configuration at each and every time step.
Correct. But for the reading, don't I need just the last configuration rather than this whole big file?
Yeah, so what you can do, you can create the configuration, you can give a beginning time and you can give a end time.
Okay.
Suppose your beginning trajectory time is 10,000 and your ending time is 10,001. So it will give the one configuration that you need.
Okay. Okay. And is there a command to find out how much disk space is used?
I
Because
have to check it whether there is a command or
no,
not.
there is some DF or something. It tells you how much space is used.
That is du space minus sh.
Right. So I think it's a good idea to keep on finding how much space is remaining, because when you keep doing simulations, lots and lots of files are created. Correct?
Yeah, that's
so
true.
one option is to keep separate directories for all the simulations.
Yeah, and once the simulations are done, you just take all this file, remove the file from the directory.
Or you can save them on a separate hard disk.
Yeah, and then when you are analyzing it, just take the files which are required for analyzing your.
Is there a way to compress all the files in a directory?
For compressing,
So, because when you do tar, no?
Yeah.
Tar and untar, is there a way to, one option is to copy all this on a separate hard disk.
Yeah,
That's the
even if you tar it or untar it,
okay.
the length of the file size will be large itself, right? So you have to anyways copy and then you have to remove the folder from that directory.
So it is best to keep it in a separate directory.
Yeah, it is best to keep it in a separate directory.
So far what we have done is an argon simulation, then water simulation, mixture simulation, and now we have done the s-peptide simulation. So the next time we will do a free energy of solvation of a molecule. Is that correct?
Yeah.
We will do free energy of solvation. We will conclude this lecture at this point. So what I would suggest all the users, whatever list of commands we have given, it is best you write it in a particular file, because it is very difficult to remember all these things if you have not practiced many times. So best is to keep a list of all the commands, and maybe they should make a directory of some of the errors they have got in the past, because that also helps you quite a lot. So once you have this list of commands, then you can execute one at a time and then proceed till the end of the thing. And what are the commands you said for plotting?
xmgrace and then the xvg file.
Right.
name.
So using xmgrace and all the xvg files, you can plot various distribution functions and analyze your results. We will conclude this lecture at this point. Thank you.